Okay, so welcome to today's class. Today I'm going to start with the third chapter of the course about the models and isometries of the hyperbolic plane. So in this chapter, I'm going to introduce three models for the hyperbolic plane, namely the hyperboloid, the upper half plane, and the Poincaré disk. So what I'm going to do is I'm going to start with the hyperboloid as a Riemannian manifold under Minkowski's form. And then I'm going to pull that the Riemannian structure, the Riemannian metric on the hyperboloid. I'm going to pull it to the upper half plane and to the unit disk, to the Poincaré disk. So arriving to the kind of well-known Riemannian metrics for the upper half plane and the Poincaré disk that pretty much behave like close to the border or close to the boundary. The distance become very long. But okay, but that will be later on. Today, I'm going to present the hyperboloid as a subset of R3, and I'm going to see that it is a Riemannian manifold under Minkowski's form, which is different from the Euclidean form. And next class, I'm going to study the isometric group of this Riemannian manifold. Okay, so what is Minkowski's form? So in R3, Minkowski's form is the bilinear form that is kind of very similar to the Euclidean form, to the usual dot product of R3, except that on the third coordinate, when one kind of pairs the third coordinates, one puts a minus sign instead of a plus sign. So this would be kind of a new sort of dot product, where I somehow modify a sign in the when considering the kind of the ordinary dot product. Now, where does this come from, right? I mean, why would I put a minus sign, right? So one of the main points is that this form, I mean, R3 with this form models Einstein's theory of special relativity in a space of in a two-dimensional space. So in a way, since Einstein's theory of relativity models the universe more accurately than Newton's than the Newton's model. Somehow, this form is actually more natural than the ordinary dot product where you have here a plus. Because this one models space-time better than the other one. So I would say this is more natural than the other bilinear form. Okay, now easy facts about Minkowski's form. It is obviously R bilinear. It is obviously symmetric, right? I mean, if you switch switch places here, the value is the same, right? So it is obviously symmetric, and it is non-degenerate by which I mean that if V is a vector with a property that for all W in the space, the pairing V with W is 0, then V is a fortiori the 0 vector. Right? And this is very easy to prove, pretty much because what appear here is they are kind of the coordinates somehow not that it's the coordinates, but they are the kind of these coordinates, they are not mixed with themselves, right? Like x2 is not mixed with y2, and similarly these coordinates don't appear mixed in any of the terms. That's kind of pretty much the reason why you can prove that it's non-degenerate. I leave it as an exercise. It's quite easy. And now one apparent disadvantage of Minkowski's form is that it is actually not an interior product on R3, unlike the ordinary dot product, the Euclidean product. So while the Euclidean product is an interior product on R3, Minkowski's form is not an interior product, and I leave it to you as an exercise. I mean, it's going to be apparent in any case during the class. Okay, and so let's say some words about the level sets of the associated quadratic form, right? So we know that every bilinear form on Rn has an associated quadratic form given by, on any vector. What you do is you pair it with itself under the bilinear form. Okay, so that's a function from R3 to R. For instance, if we were talking about the ordinary dot product, the associated quadratic form would be the square of the norm, right? Okay, in this case we are speaking about a different quadratic form because we are speaking about a different bilinear form. Okay, now level sets. So given any constant, well, the level set here, this is by definition, the level set. So all vectors with the property that when I apply Q to the vector, I obtain precisely the given constant. Okay. Now it is quite easy to see that this level set is actually the surface of revolution of a planar curve around the z-axis, and the curve is this one, right? And that's because if you have the graph of this one, then when you you see you have some curve, and then when you rotate it, this value gets replaced by this value, right? So it's quite easy. It's quite easy to see that it's indeed a surface of revolution for every c, right? For every c, and that facilitates, that makes life easier for analyzing the level sets. Okay, now what I'm going to do is I'm going to study these planar curves, because I know that when I rotate them around the vertical axis, I obtain the level sets that I want to visualize. And now this one, well, these ones you see here I can already see some like some hyperbola shape. But to see it more clearly, to see it kind of more precisely in the plane, I'm going to do kind of the standard trick from analytic geometry, which is just give a basis with respect to which this expression becomes like very simple. Okay, so that ordered basis is this one. So how to come up with this basis? Well, pretty much you come up with this basis more or less by realizing this one, right? Like that this is y minus z, y plus z. Anyway, let's look at disordered basis. Okay, and then you know, when I have a vector in R2, right? A vector in R2, but expressed in terms of that given basis, that is as a linear combination of that basis. Well, of course, I can ask, okay, what you know, I can ask what needs to happen with the scalars in the linear combination in order for the vector to belong to this planar curve, which is pretty much expressed in terms of the standard basis, right? So I ask that, and well, what happens? Well, that you see this one square minus this one square has to be the constant, right? Okay, but then here you see when I develop these squares, when I expand them, I get w square minus w square, and then I also get t square minus t square, so they all cancel, and what I here I get minus 2wt, and here I obtain minus 2wt, right? So this minus, yeah. So I obtain minus 4wt, right? Minus 2wt from here, minus 2wt from here, and everything else cancels, right? So and well, this is equal to c, of course, if and only if I have this equality, right? And from this equality, I can see that that I get hyperbolas, because you see, one fact about this basis is that the two vectors are orthogonal. So even though this is not an orthonormal basis of R2 under the ordinary dot product, they are at least orthogonal. Right, so here you can see both vectors, right? So they are at least orthogonal. Okay, so, and this means that you see that if I draw the you know, if I draw the vectors of the one-dimensional vector subspaces each of these vectors span, which is just another way of saying that I draw the WT axis, the WT axis. So the W axis and the T axis. And what happens is that whenever I draw this shape on that WT plane, that same shape is the shape of that I get if I draw the corresponding curve in the YZ axis, in the original, with respect to the original basis, right? And this is because here I have angles. But so you see here, if C is negative, so for example, if C is -4, then this is 1, right? So if C is -4, then this is 1, and WT equal to 1 is a hyperbola like this, right? Because somehow you have kind of to tilt your head so that right. Okay, and if C is negative, sorry, if C is positive, let's say 4, then this is a hyperbola like here, right here. Okay, and when this is 0, when C is 0, of course I get the union of the two WT axes. Right, so, and as I said, when I draw things in the WT plane, those drawings are also valid in the YZ plane because of orthogonality. Okay, so this means that you see when I somehow forget about the WT axis, then for C negative, this planar curve looks like a hyperbola that opens vertically. Right? When C is positive, we obtain a hyperbola that opens horizontally in the YZ plane. And when Z is 0, we obtain the union of the line y equal to z and the line y equal to minus z, right? Which that this you can see directly here, right? I mean, without having to do this. Okay, so this means that the level sets of the quadratic form, look like just kind of rotating these sets, right? So they would, for C negative, they would look like these kind of two-sheeted hyperboloids. For C positive, they look like this one-sheeted hyperboloid. And for C equal to 0, they look like this sort of degenerate hyperbola, if you will, or like some sort of boundary of a cone, right? So these are the drawings I have here. Okay, and we are going to be mainly interested in this hyperboloid, in one of these, right? Because for each negative C you have one, right? So for another value of C you have another one, etc. Right? Like a kind of like an onion, but not spherical, but kind of like with a shape of hyperbolas. Okay. Right, so we're going to be interested in one of these, namely for C equal to minus 1. And for C equal to minus 1, we have two sheets of the hyperboloid. We are going to take only one of them, right? The kind of the upper sheet. And by some abuse of language, we are going to refer to that sheet, to the upper sheet of that specific hyperboloid. We're going to refer to simply as the hyperboloid. Okay, just like by some abuse of language. I use the letter M, although M for Minkowski, right? Because we constructed it using a Minkowski's form. Although it seems that I think Weierstrass and Killing were somehow already aware of the fact that that on this set you could model non-Euclidean geometry, right? But so maybe I should use K for Killing, or maybe W for Weierstrass. I think it was for Weierstrass. I would have to check my history. Okay, so well, I'm use M for Minkowski. I don't use H because I'm going to have three models, right? And then I don't want, and then H itself is kind of for the hyperbolic plane, kind of abstractly, if you will. Okay, so well, of course, M is this one, right? But here you see here at least in Calc 3, we would kind of solve for Z, right? So solving for Z tells us that M is actually a regular surface, right? Like a parametrized surface that can be directly parametrized by the plane. And then the height is just this positive square root. And maybe at some point I will drop the plus. Just I will use it just there's room for confusion. But we are all used to just whenever we see a square root, we always take the positive one, right? Okay. This is very useful. The fact that it's a regular surface globally parametrized by R2, right? And actually, kind of you see it's actually the graph of a function from R2 to R, right? As in Calc 3. I mean, here you can see it, right? It's the graph. It's this one seen as the graph of a function, right? Of a function that to a pair x y in R2 associates this value. Okay. Now I promised that it was going to be a Riemannian manifold, right? So I have to give you an interior product on each tangent plane, right? Each tangent plane of the upper sheet of the hyperboloid. So first, what I do is kind of I express the tangent plane in terms of the Minkowski form. So here, what I do is I work with the tangent plane, not as an abstract, not in the abstract sense of differential geometry, but kind of in the concrete sense of Calc 3. So as a vector subspace of R3, right? So kind of thinking with the same sort of logic or philosophy that I'm working with the graph of a function from R2 to R. Then that graph lives in R2 times R, that is in R3, right? And then one takes, in Calc 3, one takes the tangent plane there in R3, right? As a vector subspace there. So that I think of the tangent plane in that very concrete way, not in the abstract differential geometry sense. Okay. Now, given a point in R3, I define this P orthogonal to 1. Well, what else could it be but the set of vectors that are orthogonal to the given one under the form, right? Under this form to 1. Okay, so that's how I define it, and the result is that this tangent plane is actually, if I take anything in the hyperboloid, its tangent plane, the tangent plane of the hyperboloid at that given point, is precisely the orthogonal to P. So let's see why. So the first thing is that both of them are two-dimensional vector subspaces of R3, right? So this one is a two-dimensional vector subspace of R3, let's say by Calc 3, right? And this one really is by the non-degeneracy of the Minkowski form, because being in M, P is not 0, right? P is not 0. Right here you can see, I mean, here, right? P cannot, if something belongs to the hyperboloid, it cannot be 0 because this has to give you -1. Right? Okay, and so being non-zero, it this function is not the constant 0, right? So it must have dimension its kernel must have dimension 1 or 2, right? But must have dimension one, yeah, 1 or 0, 1 or 2, but it has to be 2, right? Just by some basic dimension counting. Okay, so in other words, I solved the exercise 29 for you. Okay, so they are both two-dimensional, and this means that that then to prove the equality, it suffices to show that one of them is contained in the other. Okay, so let's do that. And let's show that this one is contained in this one. Right? That seems to be the easy part, because then because what then we would, if we decided that we want to do that this is contained in this, when you will only need to check that any element here, when you do something, you get 0. Okay, but for this one in Calc 3 we learned how to compute a basis for this space, and we learned it even if we were not informed, right? That we had learned it, because we learned how to take a partial derivatives. That's pretty much it. So so if we write our point this way, right, like as a point in the graph of a function, right? As I said earlier, a basis is given by by this, right? I mean, by taking the partial derivatives, right? Okay, so partial derivative with respect to x, partial derivative with respect to y. Yeah. So I leave it to you to think why, right? I mean, okay. I mean, that's just Calc 3. Okay. So we have two linearly independent vectors on which to test this condition, right? Okay. So we test it, right, and then the pairing of p with the first vector. Well, here you see it's x plus 0 minus this times this, right? So this one cancels with this one, and then what you obtain is really x minus x, which is 0. And similarly, when you pair p with the other basis vector, now you obtain y minus, this cancels with this, y, which is 0. So this the basis is contained, the basis of TPM is contained here. So the whole TPM is contained here, and we are done, because both of them are two-dimensional. Okay, right, and now let us show that M is a Riemannian manifold on their Minkowskis form. So maybe I should call this a theorem, but anyway, okay, I will leave it as proposition for now. So for each, first of all, for each point, the restriction of Minkowski's form to this tangent plane is an interior product on the tangent plane. So this one is not an interior product on the whole of R3, but of course, if you have a bilinear form, it maybe it happens that it's not an interior product on the whole space, but that on some proper subspaces it is, right? Think, for instance, on R3 itself. Think of the form, XYZ paired with ABC to be XA plus YB. Right? So in the formula, the third coordinate is not present. So that, of course, is not going to be a an interior product on the whole of R3, but it is an interior product at least on the XY plane, right? So on a proper subspace, it is, even though it is not an interior product on the whole thing. So similarly to that, this one, even though it's not an interior product for R3, it's going to be an interior product for each of these vector subspaces. Okay, so that so far tells me on each tangent plane you have an interior product, right? And the only thing missing for being a Riemannian manifold is that when you vary the point on the space, which is the hyperboloid, the interior product varies differentiably, right? So one way of saying that is that when we let P vary, the matrix that represents the corresponding bilinear form, namely the corresponding interior product, is when P varies, that matrix or the entries of that matrix vary differentiably with P, so that the function that associates to each P this matrix is of class C infinity. Okay, so we're going to see that. So let's prove first that the Minkowski's form restricts to an interior product in each tangent plane. So as we already saw, this one is R bilinear and symmetric, so each GP is of course R bilinear and symmetric, right? That those are properties that are inherited on the restriction. Okay, so now we write. So now I'm going to write, instead of x, y, z, I'm going to write the point as a, b, c. So later on, so somehow these computations, in these computations, x becomes a and y becomes b. Okay, so we will just keep that in mind. And now I take a tangent vector, a non-zero tangent vector, and I write it as x, y, z. Okay, so because of this proposition, namely because of the containment or of the inclusion we proved, we have this equality, that is V and P are orthogonal with respect to Minkowski's form. Okay, and now to continue, let's recall Cauchy-Schwarz inequality for interior products. So if I have a real vector space with an interior product, then for any pair of vectors, the absolute value of the dot product, well, the square of the absolute value of the dot product, is less or equal than the product of the squares of the norms, right? Okay, so of course, I'm not going to apply this theorem to GP, because I don't yet know that GP is an interior product. But you see, I can apply it for R2 with the ordinary dot product. That I can do, right? And when I do that, and I do it for the vectors x, y and a, b, which live in R2, I obtain that the square of the norms, the product of the squares of the norms, is greater or equal than the square of the dot product. So I am applying this Cauchy-Schwarz inequality. Now, this one, you see, because of this equality, if I pass zz to the right, I obtain that this is equal to z squared c squared. Yeah, so if I pass ZC to the right in this equality, what I obtain is this one square is equal to Z square C square. Right, so I'm here. Now, ZC, you see, C square, um, so since P is in M, what I obtain is, and I think it's here, right? So since P is in M, A square plus B square plus minus C square is minus 1, right? So C square is A square plus B square plus 1. So I can substitute this one with this one. Okay. Now now I distribute Z square. Right. So I distribute it here. And you see, and now I look at this inequality. This is greater or equal than this, right? So I can pass Z square times A square plus B square to the left, subtracting, and factor A square plus B square as a common factor, right? So what I obtain is that this is greater than Z square, right? So this one is already passed to the left. Okay, so this is what I obtain. And then this automatically tells me, well, I took V to be non-zero, so at least one of its entries is not zero, right? So if Z is not zero, right, so this thing is positive. And then I know that this is positive, and so this has to be positive, right? But this is precisely GP of VV, right? The pairing of V with itself. So this is positive. Okay, and if Z is equal to 0, well, I know that at least one entry of V is not 0. And Z being 0, then this means that the pairing of V with itself is just x squared plus y squared, which is then greater than 0 because one of the three has to be non-zero. So in any case, I obtain that the pairing of V with itself is positive. And this finishes the proof that GP is an interior product in this tangent plane, right? Because it's R bilinear, symmetric, and this is a positive definite, right? Okay, and now finally, you see, when you compute the matrix of GP with respect to the basis that I computed before, which is this one, but as I said, with x replaced by A and y replaced by B, you obtain this one, right? And I mean, and how is that matrix, this matrix defined? Well, you take the elements of the basis, and then you pair them among each other, right? So the first one paired with itself gives you this. The second one paired with itself gives you this, and the first one paired with the second one gives you this, which is equal to this by symmetry. Right? Okay, and then when you make that computation, you see A and B. I mean, these four entries vary infinitely differentiably with A and B. Right? So we obtain a Riemannian structure on the hyperboloid. Okay, now as I said at the beginning, next time I'm going to compute the group of isometries. So today was okay.